Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to discuss some topics in the context of MD simulations. We have already talked about the use of potential cutoff in calculating intermolecular forces, but when we try to apply these techniques for MD simulations, there are certain issues that we need to take care of, and there are also other methods by which we can improve upon the calculation of forces in a very economical and speedy way. So, the context of today's discussion is going to be how to decide potential cutoffs and how to use neighbor lists so as to increase the speed of MD simulations. To recall the fact that in the MD simulations, the most of the computational time goes in the calculation of pair potentials or pair forces. So, this is an algorithm that shows the looping over n into n minus 1 number of pairs when you have n number of particles in the system. So, the first loop is over I is equal to 1 to n minus 1, and the inner loop goes from j is equal to I plus 1 to n. We do I plus 1 to n because we do not want to double count the force calculations, and then we calculate the interparticle distance Rxij, Ryij and Rzij, and then we calculate the square of this distance, and then we use, let us say, Lennard-Jones potentials, and then we sum this potential over all the pairs. So, this is the unoptimized version of force calculation in a particular time point in the MD simulations. So, now the question is, how can we reduce this number of force calculations in the MD simulations? One possibility is by using what is called this potential cutoff. This is something we already discussed, because we said that out of this n square order of operations, if the potential is a short range, you are not going to expect each molecule to interact with all the other molecules in the simulation box, but rather the potential is influencing only up to a particular distance, which is shown here. Suppose if we take one particular atom here, and then you can think of a spherical radius of RC, and then you can calculate the intermolecular forces between this chosen tagged atom with other atom within this particular circle. This is a 2-dimensional picture, but in a 3-dimensional picture this is going to be a sphere, and then the simulation box will be a cube. So, within a simulation cube we can take a particular particle and then draw a particular sphere of radius RC, and then consider only particles within that particular region to calculate forces. In the previous loop here, we would have actually looked at all combination, all the particles we would have taken in calculation of forces, but now we see that the potential is a short range. So, we do not have to really go all the way up to this atom or this atom, because it is not going to be significant enough, because the potential falls in a very short range. So, mathematically what this means is taking the Lennard-Jones potential only up to a distance of r equal to Rc, and then setting this potential equal to 0 for r greater than Rc. So, this is called the simple truncation. So, this is the potential cutoff we have discussed in one of the previous classes. It is shown in this graph, the variation of the potential as a function of r. You can see that when we cut it off at r equal to Rc, that is this point. So, you can see the potential is not equal to 0 there, we are actually cutting it here, and then from here onwards the potential is 0. So, we see that there is a discontinuity in the energy at r equal to Rc. And then if I calculate force, because in MD simulations we use the forces to update particle positions and velocities using Newton's law or Hamiltonian mechanics. So, calculation of force also shows a discontinuity at this particular point. The dotted line here is the force, and the continuous line here is this potential, the Lennard-Jones potential in this case. and Lennard-Jones potential is taken as an example to illustrate this concept. So, we can see that both energy and force both are discontinuous at r equal to rc. And what is the meaning of this discontinuity? So, whenever a pair of particle moves away from here to here or from here to here, then you see there is a sudden discontinuity in the energy as well as there is an impulse because of the force discontinuity. And the consequence of these discontinuity in force and energy is that the energy will not be conserved in this particular simulation, because every time a particle comes or moves, we are going to lose some energy there. But we already noted such a simple truncated potential can be corrected for energy using what is called the Tail correction by integrating the potential from RC to infinity, and then in the case of Lennard-Jones potential we can substitute and we can get an analytical expression for the energy. So, the energy that we are losing by simply truncating the potential here can be compensated or corrected by adding a tail contribution at the end of the simulation. And similar correction is also possible in the potential in the pressure as well. However, these methods are quite good for Monte Carlo simulations, because in Monte Carlo simulations we do not use forces, we use only the potential energies. But when we try to use this approach, simple truncation in MD simulations, we see that this discontinuity in force causes instability in numerical solution of the equation of motion. So, in MD simulations, simple truncation often leads to a problem in convergence, problem in instability of the simulations. So, such an approach is only applicable for Monte Carlo simulation, not for MD simulations. So, what is the next thing we can do? The next approximation we can do is we truncate the potential and then we shift the potential. So, what does this mean? So, basically we take this potential. So, this is our original Lennard-Jones. It goes to 0 at a very long distance, I mean at maybe about, it asymptotically goes to 0. So, this is the full LJ. Then we talked about the truncated potential in the previous slide, where we take the potential and cut it here and then set equal to 0 from here onwards. So, this is called simple truncation. So, in the truncated and shifted, what we do is we truncate at this point and then you move this potential up by subtracting the potential of this much amount, so that this becomes simply, it goes to 0 at r equal to rc itself. So, we are truncating at this point and then we are shifting by this cut potential, so that at r equal to rc itself the potential goes to 0. So, mathematically you can show that for r less than or equal to rc, the potential truncated and shifted potential is given as the Lennard-Jones full potential minus the Lennard-Jones potential calculated at r equal to rc. So, that would be the value right here. So, this is going to be ULJ at rc. So, this much amount is now subtracted, so that this point comes to 0 here at r equal to rc. So, what is the advantage of doing this? We can see that in this approach the energy smoothly goes to 0 at r equal to rc because of this additional shifting. So, in this simulation then we do not have a problem of energy convergence inside the simulations. However, we want to do simulation with this potential, but we are actually doing simulation with this potential. So, the property would be different between these two, and that has to be corrected as well. So, for correction we see this the tail correction can be done as before for the truncation part and then for the shifting part. So, you can see that in the shifting part what we are trying to do is we are shifting by an amount of ULJ at RC, and then we are multiplying by a factor of NC, where NC is nothing but the number of atoms or number of neighbors within a distance of RC, because that many number of pairs we would have lost by subtracting this energy. So, this is coming from shifting contribution and this comes from a truncating contribution. So, this is about energy. What about the pressure or the force? So, if you look at this potential and if I take the derivative of this energy with respect to r, you will still see that the force is still discontinuous, because we are only adding a constant term. So, energy wise it goes to 0, but then if I take the derivative, you will still have discontinuity in the force. So, if I draw the force here, you will still have discontinuity at this point, and this could also lead to instability in numerical simulation. So, one has to watch out for any abnormality in the convergence of equation of motions because of the fact that the force is discontinuous. So, we have seen two possibilities. One is simply truncating it, where both energy and force are discontinuous, and energy correction can be added via long range correction. However, the force discontinuity might cause numerical instability in the algorithm. And the next possible approach is to truncate and shift. So, in this approach, we truncate the potential at some cutoff, and then we also shift by the amount equivalent to the potential at RC. Thereby, we are able to smoothly, we can make the energy to smoothly go to 0 at R equal to RC. However, the force is still discontinuous at R equal to RC. Then the next approach is what is called the shifted force potential. So, what we are going to do now is we are also going to shift the force so that the force goes to 0 at R equal to RC. The way you do that is, so this is the potential where I said that the force is discontinuous, right. So, basically we try to add a force component so that this goes to 0 right here by adding a particular amount of force. So, that is shown here. So, this is the full Lennard-Jones potential. This is now truncated, shifted, and then also additional term is shifted, which is linear in R. And then you can, if you take the derivative of this potential and then substitute at R equal to RC, you will see that the force also goes to 0, and at this particular point, that is at R equal to RC, both energy and force, they both go smoothly to 0 at R equal to RC. Now, this simulation, the property that you estimate from this simulation is going to be quite different from the simulation that we actually want to do with full Lennard-Jones potential. So, this has to be corrected for shifting, truncating the forces as well, and that correction involves little tedious process. We are not going to discuss that particular method here, but when you use any commercial software like GROMACS or LAMMPS, you will have a choice of what kind of truncation to use. So, most of the times we use either shifted force or truncated and shifted intermolecular interactions to run the simulations. So, these are some of the possibilities of managing the potential cutoffs in with respect to MD simulations. As far as MC simulations are concerned, simple truncation is good enough. Now, what have we achieved by having this potential cutoff? To see that, we again go back to the force calculation in a double loop here, I going from 1 to n minus 1 and j going from I plus 1 to n. So, in this case, what we do with this potential cutoff or truncation or shifted force, so after we calculate the Rij square here in this step, we check whether this Rij square is less than or equal to the cutoff square. If so, then we calculate the forces here. So, what this basically means is, even in the presence of the potential cutoff, whichever way it is, truncated or shifted force, in all these three cases, we still have to do n square operation to find the pair distance Rij. Only after that, the saving we are getting in terms of computational time is in this step, where we are going to take only certain pair which satisfy this condition. Otherwise, we are still getting n square operations in the entire algorithm. So, the question is, can we improve upon this even further? Yes, it is possible, and in this context, we will be looking at what is called this neighbor list. So, we are going to move to a different kind of an approach. Apart from having the cutoff, can we do something more so as to reduce this operation of n square calculation? So, one such approach is known as what is called as Verlet list. So, in this Verlet list, you can see that we have taken a target particle of 1, we are tagging it here, and then we defined as before a cutoff, potential cutoff RC. That means we want to take only the neighbors within this particular circle to calculate interaction between 1 and 2, 1 and 3 and 1 and 4. And any particle lying outside this circle of RC is not considered for the calculation of forces. This we know already. However, in Verlet list what we do is we define an additional cutoff radius, it is called a skin width RL, and this RL is basically an additional cutoff which can be typically defined as the potential cutoff RC plus some 3.3 times sigma or maybe plus 0.5 times sigma in the case of Lennard-Jones potentials. So, we are actually adding an additional thickness or a buffer zone, and then we keep track of how many particles are there in this buffer zone. And what we are going to do is we are going to keep a list of neighbors for each particles within this radius of RL, even though we need only neighbors within the distance of RC. And the reason for doing that is that over a period of MD simulations, you might have some these molecules here coming inside and going outside. So, it is good to keep a record of the next nearest neighbor. So, we do not have to every time calculate the neighbor list. So, with this you can see that we basically create two arrays. The first array here is called the list. So, this list is basically a one dimensional array. It saves all the neighbors up to the of all the neighbors of the atom 1. For example, in this particular case, you see this entry from 1 to 41 of the list contains the information of all the neighbors of the first atom. So, that is the first neighbor is particle 2, particle 3, particle 5. So, these are all the neighbors of the first atom. At the end of this list, then we start adding the neighbors of the second atom from here to here, and then from here onwards we are going to add the neighbors of the third atom. So, I can actually run this list so as to have the neighbors information of all the atoms, atom 1, atom 2 and atom 3, and instead of saving them separately, we are going to just put them in a, we just combine them all together in a sequential fashion. So, the topmost would have a block of neighbors of the first atom, below that would have the neighbors of the second atom, and subsequently other atoms neighbors are stored. So, that is called the list array. So, then whenever we want to calculate the force calculation and we want to iterate over all particles and their neighbors, what we need is we need an additional array called endpoint, and this will have this endpoint basically has an element for each molecule in the system or each atom in the system. Okay. So, you can see that endpoint 1, 2, 3, 4, it goes all the way up to n. For each molecule, this endpoint array has an element, and what this array element is nothing but the address of the first neighbor. For example, if you look at this endpoint of 1, it basically means it refers to 1, and this 1 is the first element of the list contains the first neighbor of the first atom, and from here the next would be the first neighbor of the second atom is in the 41st position. Okay. So, that is so if you look at the 41st position of the list, this contains the first neighbor of the second atom. What this means is from 1 to list of 40 would be the neighbors of atom 1. Similarly, if you go to atom 2, the first element is in list of 43, which is atom number 3. And then if you look at endpoint 3, that means the first neighbor of the third atom is at the 83rd position. So, you go to 83rd position. So, this is the first neighbor of the third atom. So, in the for the neighbor of second atom, all we need to do is go from 41 to list of 82. and all this will have the neighbors of the second atom. So, so to iterate this one more time, so in the case of Verlet list, what we do is we collect information of all the neighbors at any given point of time. Okay, at any given point of time, we first collect the neighbors of all the atoms, and then we create a list, and the list contains all the neighbors of all the atoms in a sequential way, stored in a sequential way. So, first we populate all the neighbors of the first atom, then we populate all the neighbors of the second atom, and so on. So this is a very long list, contains information of all the neighbors of all the atoms. Then to find out what range are the what is the range of this list array which contains the information of the neighbors of a given atom, is given by an additional array called endpoint array that always points to the location in the list array where the first molecule of that particular atom is. So in this case, this endpoint of 1 basically means this index here is an address for the list, and then that will tell you which atom is the first neighbor. Similarly, endpoint of 2 will tell you an address 41 in the list array, which gives the first neighbor of the second molecule, and endpoint 3 addresses to 83, and this 83 number is the address of the list in which the first neighbor of the third molecule is present. And then with this, you will be able to loop over the neighbors of the first molecule, second molecules. Okay. So then this particular list, you don't have to really update at every point of time. You generally update this once in 10 or 20 MD steps. That is because over this 10 to 20 steps, the atom that are coming inside would be mostly atom coming from the skin area, skin region, not from outside. So in fact, you can also, what we can also do is we can even automate the way that list should be operated by looking at how much distance these molecules have actually gone over a period of time. So there is a way to automate this list, or sometimes we can also do it once in 10 or 20 steps. So what is the use of such an approach is actually illustrated in this particular examples. There are two different kinds of simulations. In the top here, what we are seeing here is we have looked at no list condition. That means we will be doing n square operations, okay, without any just only a truncation potential, no lists, and then set of additional simulations where the Verlet list is constructed with a different list radius. Okay, so this is basically the RL, and this basically tells the interval with which this list was updated. And then we have two system size, one is at 256 particle, the other one is 500 particles. That means two different system size of the simulations. And what we are trying to compare here is the time, the CPU time per MD step used in these simulations. So the reference case would be that if you don't use any Verlet list, for this 256 particles, the time taken per one step is 3.3, whereas in the larger system 500, the time taken per step is about 10 unit of time. So here the time is in a non-dimensional units of Lennard-Jones units. And then if you, from no list, if you go to a Verlet list of a list radius 2.6, you see that there is a small saving in the CPU time per step for 256, and this effect is even more dramatic as you go to larger system. When you go from when you go to 500 particles, the time taken per CPU step goes from 10 to 4.93. That is roughly about 50% time saving in the computing power. And then if you try to increase this further from 2.6 to 2.7 and blah, blah, and etc., and you can see what is the influence of the time taken, CPU time taken per step, and you can see that increasing the R list is not really beneficial beyond certain list radius. Okay, so for example, if you look at this 256, so I think beyond 2.6 there is not much improvement. In fact, there seems to be small increase in the CPU time. Similarly, if you look at this larger system 50, a dramatic change in the saving of time happens only going from no list to 2.6 or maybe up to 2.7, and beyond 2.7 there is not really a big difference in the time saving. So you might wonder, why is that increasing the list radius increases the time beyond certain optimum list radius. So that is because if you keep the list radius big, Okay, so if you keep this RL big, then you are basically having more number of neighbors stored, and then you have to search through these set of neighbors, and those neighbors may not be so useful in the calculation of your forces. So that's why there has to be an optimal radius. So if you increase this radius R list too much, then we are having too many number of neighbors which are not significant in calculating the dynamics, but still we are bookkeeping them, and that's what leads to an extra computational cost trying to increase this. You can see that, for example, if you go to 3.5, which is quite a large value of high value of list radius, you can see that the time taken for per step is kind of increasing again. So it means in Verlet list there seems to be an optimal list radius at which maximum computer saving is possible. And this is another set of simulation study where the simulation is done with the two different densities, and again for each of these densities we are talking about two different system size, 108 particle and 256 particle. And here we are looking at what is the relative number of time steps executed for a given computational time. So the question that we post here and the question we post here is different. In this case, we ask how much CPU time per step is required, and we comparing the effect of R list. In this example, for a fixed computational time, CPU time, we ask how many MD steps were possible. So clearly, if you have a faster algorithm, you could have done more steps, and that is what is evident here. You can see without list, you are able to do only some 6 and an average some 6.7 steps, whereas with list you are able to do some 9.7 number of steps for a given CPU time. And then you can also see that the effect is more dramatic in the case of a larger system compared to the smaller system. So what this means is, if you want to do MD simulation of a larger system compared to without list, having a Verlet list of an optimal cutoff radius helps in speeding up your computer simulations. So these are some of the important things to remember when you either write your own MD code or when you use some of the MD open codes available in the literature. So the next approach, so we talked about Verlet list, and another approach even more often used compared to Verlet list is called linked list based cell lists. So the approach, the idea here is you take this entire simulation box and then you break them into small cells. Okay, you divide them into small cells. We are not physically dividing them, we are basically virtually dividing them. We are just to bookkeep what are the neighbors present in those small cells. So here in this example, a 2D simulation box is shown. So the entire box is this, and then this entire box is divided into small cells of edge length RC, and then we give a number for each of these cells. So this is the first cell, second cell, third cells, etc., etc. In a case of a 3-dimensional box, you would have m cube number of cells, and then the edge length of the cell is either RC or more than RC. So now the advantage of doing this is, now we can actually, when we try to calculate the forces, we know where exactly to look for the neighbors. For example, if you consider this particular cell 13, and any atom present in this particular cell would interact with all the other atoms present, in the same cell, and also neighbors present in the other cells like 7, 8, 9, 12, 13, 14, 17. So these are all, you might have some distribution of neighbors in these neighboring boxes. Okay, so neighbors of any molecule in cell 3 will be only in 7, 8, 9, 12, 13, 14, 17, 18 and 19. And if you say what is the average number of molecules per cell in this kind of 2D, you can find this is the total number of particles and divided by the m square, and m square is the number of cells in a 2-dimensional box. So that would be an average number of neighbors in each of the cell. Whereas in the case of a 3D, the number of particles or number of molecules in a given cell would be total number divided by m cube, because it is in 3D. So, this NC here is an average number of particles in a given cell. And then when we try to calculate the forces, for example, if we take one particular example here, then the number of pair calculation is going to be half, because of double count. To avoid the double counting, we have this factor of half, 9 times NC times N. So, this is going to be the total number of pairs in 2 dimensions. Why 9? Because you can see that in this case there are 9 surrounding box, including the central cell. So, and then there are 9 cells, and each cell might have an average of NC, and then you are going to repeat this for all the N particles in the entire system. So, the factor is half times 9 times NC times N pair in 2 dimensions. In the case of a 3D, in the 3-dimensional box, the number of neighboring cells would be 27, okay, and then half is to avoid double counting. NC is this number of average number of particles in a given cell, and then you multiply by the total number of particles. So, you are going to have an order of NC times N. So, the calculation of force has come from N square to an order of N. Okay. So, that is a good saving in the calculation of MD simulations. So, now the question is, how do we map the number of neighbors or the identity of the neighbors present in the each cell. So, remember, you have to remember, this is a central simulation box. We are not talking about periodic boxes, we are talking about within the simulation box what is the distribution of molecules. Do not confuse this with the periodic images. This is a central simulation box. The simulation box itself is divided into small cells, so that we can remember or we can bookkeep the neighbors of or the molecules in each cell, and that can be used in calculating the forces. So, in this example we are showing only 2 such cells. Okay. Let us take 2 cells, this cell and this cell. So, this is basically a part of the central simulation box. This index 1 here is index for the cell, and all these elliptical objects that you see here could be the molecules of interest. So, what we do here is we want to basically bookkeep the molecules in each cell, and then we should be able to retrieve them, find their identity and use them for calculating forces. So, to do that we create an array called head, which has one element for each cell. So, if there are about m square cell, then you will have so many elements in this particular for this particular array head. It basically is something that refers to the head of the chain. So, in this particular example of 1, you can see that there are particle 1, 2, 5, 7, 8. So, they are actually considered as a part of a chain, and we can actually see that 8 refers to 7, 7 refers to 5, 5 refers to 2 and 2 refers to 1. And then if you follow this chain, you can actually reach all the molecules in this particular cell. Similarly, if you go to the cell 2, all the atoms present here are 3, 4, 6, 9, 10, but then they are actually connected via a kind of a virtual chain. If I know the atom or molecule 10, it refers to molecule 9, and then it refers to 6, and the molecule 6 refers to 4, and 4 refers to 3, and that is the end of it. So, this is called a linked list, storing the information of atoms and molecules in a given cell using a linked list. So, if I know one particular molecule in that particular cell, and using that I can actually reach out who are the next molecule in this particular cell. So, we have a head that refers to the first element of each cell, and this will tell you the identity of one of the molecules in this cell, and this identity can be used to address the element of another cell called a list, and the list contains the identity of the next molecules in the cell. So, this is basically a simple linked list algorithm. And to see how this works, it works on basis of 2 lists, 2 array. One is the head, which has element for each of the cell in the system, and the list is basically contains the information of the molecules in each of those cells, and here position is the array index. So, for example, in this example there are only 2 cells, 1 and 2. Okay. So, you can see that the head has only 2 elements. Suppose if you consider the second cell, and the head of 2. So, head of 2 is equal to 10 in this particular example. So, what it means is this 2 here is the index for the cell that we are talking about, and this element 10 refers to the first molecule in this chain. Okay. So, that is 10. So, then with this 10 what we are going to do is we go and then look at the 10th position of the list array, and that points to a number called 9, and the 9 is the next molecule. Then we take this 9 and then go to the 9th position and then come back to the list, and it refers to another atom called 6. So, we go to the 6th is the next neighbor in the cell, and then we go to the 6th position of the list, and that tells you 4. Okay. So, that is the next molecule, and then we go to the 4th position of the list, and that points to molecule 3, that is this. And then if you go to the 3rd position of the list, it shows 0. That is where you have to stop, because you have reached the end of the chain, and all the neighbors in this particular, all the molecules in this particular cell 2 are now identified. So, now if you want to calculate the interaction with all the molecules present in this cell 2, you basically follow this particular linked list, so that you can get all the molecules 10, 9, 6, 4, 3, etc. using this 2 array called head and list. So, this is something we have done for the second cell, and then let us say do for the first cell. So, the first cell's head, the head of 1 is equal to 8. Okay. So, we go to the 8th position of the list array, and it points to atom 7. So, the first atom is 8, and then it points to the atom 7, and then we go to the 7th position and it points to atom 5. So, that is our next atom, and then we go to the 5th position and it points to atom 2. So, we take the molecule 2, and then we go to the 2nd position and then it points to 1. So, that is the next neighbor, and then we go to the 1st position and then it points to 0, that is where you stop. So, by this linked list algorithm we are basically able to start from one molecule in the cell and then reach out all the other identity of the other molecules in the same cell, and this can be used to calculate the forces between an atom and all the molecules in a given cell. So, this can be very easily coded using linked list algorithm, and in MD simulation, broadly speaking, most of the simulations work with this kind of linked list algorithm, sometimes even with a combination of Verlet list also. So, here is a comparative study. What it says is the computational time, CPU time versus the system size for Lennard-Jones particle. Here we are actually comparing the performance of all the algorithms. The first algorithm is this n square algorithm, which uses no Verlet list or no cell list. It just has only a potential cutoff, the bare minimal algorithm. And if you see that, that is basically the circle here, and you can see that as n increases, tau also increases very rapidly. And the next thing to compare with would be the Verlet list. So, same system under same thermodynamic conditions, you apply the Verlet list for calculating forces and then compare the relative performance. If you see when the n is very small, you can see that this the triangles here all fall under this, below this n square algorithm. So, you get a good saving of computational time up to some thousands of particles. But the moment you go to larger system size like 6000 or 7000, you see that the Verlet list becomes more expensive than simple n square. So, that is because when you go to very large system size, as I said before, you have to manage the list which is very big, because it will have information of neighbors of all the n particle system, and then it becomes prohibitively difficult to manage, to search through, to sort this list array in the Verlet list. So, Verlet list is not very good algorithm for very large system size beyond 5000 particles. On the other hand, if you look at the neighbor list, so here the example is shown for two different densities. Suppose if you take the low density limit of 0.2, so that is the squares here, you can see compared to the Verlet list and n square algorithm, the amount of time required for the cell list is actually orders of magnitude smaller. So that's why it is the most sought after algorithm in managing force calculation in MD simulations. And you can also see, even if you increase the density to 0.8, that means the density more means the number of neighbors are going to be more, and you can see whether there is any density dependence. And you can see that even with the density of 0.8, the computational time looks very similar to each other. The difference is between the n square algorithm and the neighbor list, which seems to be quite advantageous. And then another comparison we are making is a combined Verlet list and neighbor list, and you can see that for larger system size, it's still the neighbor list win over either n square list or Verlet list or even the combined list. So this kind of a comparison tells us that depending upon the system size, what algorithm one should be using in MD simulations. So to summarize, what we looked at in today's class is that with regard to MD simulations, what are the possibilities in using truncation of the potential so as to improve the computational speed. One approach is to use potential cutoffs, but then potential cutoffs leads to energy convergence problem, force discontinuity, numerical instability, and we have to be careful in taking care of such issues. That's one angle. The other perspective is once we have decided what kind of cutoff to be used, and then we have to manage the information of the neighbors, for which we consider two algorithms. One is Verlet algorithm, another one is a cell list algorithm. Well, Verlet algorithm is very simple to implement because it just stores the information of all the neighbors in a very long list. It is a very good algorithm as long as the number of particles is, let's say, below 500. But the moment you go to larger system size, you see that the Verlet algorithm is not effective because of the fact that you're going to bookkeep a lot of neighbors in the list, and then you have to loop over the list. It adds to a lot of computational cost, bookkeeping cost, whereas the other algorithm, neighbor list based on linked list, seem to be more effective in saving computational time, because it actually breaks this and divides this entire simulation cell into smaller cells, and then we keep record of the information of the molecules in the cell via linked list, and it actually helps us to search through the molecules in the cell in a much more efficient way, and the net effect of this is a saving of computational time in order of magnitude. So if you write your own code or if you use any commercial software, you will have a choice of using neighbor list or a Verlet list. Always go for a neighbor list, and that would give us enormous saving in computational time.